A SCADA system does not fail only when servers crash. That is the visible failure, the easy failure, the failure everyone can point to. But the more dangerous failure happens quietly, when operator screens update late during process upsets, when alarms arrive out of sequence, when historians lose resolution, when redundancy transfers slowly, when communication recovery floods the system, and when future expansion exposes that the architecture was designed too close to its limit. This is why SCADA performance evaluation must never be treated as procurement paperwork, feature comparison, or vendor compliance language, because the real purpose is not to confirm that a software platform has screens, alarms, reports, trends, clients, redundancy, and historian functions. The real purpose is to prove that the delivered architecture performs under normal load, peak load, abnormal operation, communication failure, server failure, recovery, cybersecurity constraints, operator concurrency, and future expansion. You are not buying graphics, tags, alarms, and servers. You are buying operational certainty, and that certainty means operators can trust that screen values are current, alarms are timely, commands reach the field, historian data is complete, standby systems can take over, alternate control rooms can assume authority, and future expansion will not turn the system into a bottleneck. The first engineering parameter is real-time database spare capacity, because the real-time database is the live nervous system of the SCADA environment, carrying process variables, equipment status, alarm states, calculated values, communication health, command feedback, quality indicators, interlocks, diagnostics, and derived operational logic. If present operation requires 40,000 live points, the design should not be built around a 45,000 point architecture and called optimized, because that is not optimization, that is fragility disguised as efficiency. A minimum 50% spare real-time database capacity should be treated as a practical design margin, because future stations, diagnostic points, calculated tags, cybersecurity monitoring tags, communication quality tags, redundant tags, virtual tags, interface tags, and analytics tags will always appear later. And if the database has no reserve, every expansion becomes a negotiation. Every diagnostic improvement becomes a burden, and every cybersecurity addition becomes a compromise. A point is never just a point. A slow digital status is not equal to a fast analog value with scaling, alarming, historization, deadband, quality processing, display references, and operational consequence. So the correct question is not how many points the software can theoretically support, but how many points this delivered architecture can support while maintaining alarm reporting, screen updates, historian logging, command execution, redundancy synchronization, communication polling, CPU margin, RAM margin, disk performance, and network loading under peak and degraded conditions. The second engineering parameter is RAM spare capacity, because memory pressure does not always create dramatic failure. It creates slow graphics, delayed alarm loading, sluggish trends, failed reports, paging dependency, unstable client behavior, inconsistent primary and standby performance, and intermittent faults that are difficult to diagnose, especially when virtualization introduces memory oversubscription or mixed server roles. A minimum 30% free operating RAM should remain available under peak tested load, and this must apply across real-time servers, historian servers, database servers, HMI clients, engineering workstations, web gateways, communication servers, and virtualization hosts, because minimum hardware recommendations only tell you what may start the software, not what will sustain stable operation during alarm bursts, historian queries, engineering access, remote sessions, backup activity, antivirus scans, reports, and redundancy synchronization. The third engineering parameter is CPU loading, because server processors carry real-time database processing, protocol drivers, alarm processing, historian compression, display serving, scripts, calculations, security services, redundancy heartbeat, reports, operating system processes, remote access, and background services. A server running at 65% CPU during normal operation may look acceptable until alarms burst, communication links recover, historian backfill begins, clients reconnect, and redundancy synchronization occurs simultaneously. A strong design target is maximum 30% CPU load at full operating load, because critical infrastructure needs processing margin when conditions stop being normal. High CPU load creates alarm latency, screen lag, delayed polling, slow commands, historian backlog, failed synchronization, and operator distrust. And once operators believe screens are late, they hesitate, cross-check, call field personnel, and lose confidence in control room authority. The fourth engineering parameter is historian capacity, because the historian is not only a trend database, it is the memory of the asset, supporting maintenance analysis, incident investigation, compliance review, custody review, energy optimization, performance monitoring, root cause analysis, shift handover, and long-term operating knowledge. After an event, nobody asks whether the trend screen looked attractive. They ask whether the event can be reconstructed. A minimum 100% spare historian capacity is sensible because history always grows through more points, higher sampling rates, longer retention, calculated values, event-based logging, reports, analytics, alarm journals, backfill, and store and forward records. Historian sizing must include write rate, query response, trend rendering, archive strategy, compression, backup, restore, retention, and recovery, not just disk volume, because storage without retrieval performance is not useful operational memory. The fifth engineering parameter is configurable SCADA point capacity, because 65,000 configurable points may be a practical baseline for medium and large systems, but point count without behavior is misleading. Points must be classified into analog, digital, calculated, alarmed, historized, command, diagnostic, communication quality, cybersecurity, and interface classes, and every class must have scan rate assumptions, historian assumptions, alarm assumptions, display assumptions, and communication assumptions. The sixth engineering parameter is operator and client capacity, because high user capacity is not only about control room operators, it includes maintenance users, engineering users, remote support users, view-only users, cybersecurity users, management dashboards, emergency response users, and temporary support access. And uncontrolled client loading can overload display servers, increase query load, consume bandwidth, slow alarm pages, increase cybersecurity exposure, and degrade control room performance. The correct question is not how many users can log in, but whether every user can receive timely, role-based, secure, auditable, and stable access without affecting the operators who actually control the asset. Control operators are not the same as dashboard viewers. Engineering stations are not the same as maintenance tablets. Remote support is not the same as command authority, and view-only access should not consume the same resources as primary control operations. The seventh engineering parameter is RTU capacity per server, especially for pipelines, water systems, terminals, utilities, tank farms, remote stations, and geographically distributed infrastructure. A system may configure many RTUs, but if it cannot pull required data at required rates, handle weak communication, survive link failures, process alarm bursts, and recover cleanly after communication restoration, then the architecture is not truly capable. Remote telemetry is not clean, fast, and local. It includes fiber links, radio links, leased lines, cellular paths, satellite paths, serial links, firewalls, gateways, latency, packet loss, intermittent recovery, and delayed event bursts. So the SCADA server must survive RTU silence, RTU recovery, buffered event floods, bad quality data, delayed timestamps, and command feedback uncertainty. The eighth engineering parameter is burst event handling, because normal operation proves very little. Abnormal operation is the real examination, and a burst handling requirement such as 1,000 events with a defined event per second rate tests whether the system can process rapid operational truth without hiding, delaying, duplicating, or disordering that truth. During event storms, the system must preserve timestamp integrity, event sequence, alarm priority, acknowledgement status, shelving status, operator comments, audit trail, and historian event journal consistency. Poor burst handling causes delayed alarms, duplicate events, missing events, frozen alarm pages, operator overload, weak incident reconstruction, and confused decision-making during exactly the period when clarity matters most. The ninth engineering parameter is complete point update time, because a 2-second update boundary is not only a speed metric, it is an operator confidence boundary. And when operators trust that screens reflect the process, they act decisively. But when they suspect delay, they hesitate, cross-check, call the field, delay commands, and lose confidence in the control room picture. Point update time depends on field scan time, protocol efficiency, network latency, server load, display subscription, client rendering, database optimization, and communication driver configuration. So engineers must separate field scan time, server database update time, display refresh time, and total operator visible update time. Critical process values may need faster scan classes, while slow diagnostics do not, and forcing every point into the fastest scan class only overloads communication without operational value. The 10th engineering parameter is alarm and event reporting time, because a late alarm can be worse than no alarm when it creates false confidence. The operator believes the system is quiet while the process has already moved. So alarm reporting must be tested from field detection through controller or RTU timestamping, communication transport, SCADA acquisition, alarm evaluation, display update, annunciation, and event logging. 2 seconds or better from source event to operator visible alarm should be treated as a serious requirement subject to field communication constraints, and sequence must be preserved because during abnormal operation, what happened first can be as important as what happened at all. Therefore, source-to-screen latency, burst conditions, communication recovery, timestamp accuracy, and event journal integrity must be verified. The 11th engineering parameter is HMI screen update performance, because an attractive graphic that updates late is operationally weak. Operators do not need decoration during an upset. They need truth, hierarchy, contrast, clarity, response, and cognitive discipline. And overloaded screens filled with unnecessary animation, heavy scripts, embedded queries, decorative objects, dense data, and unclear priorities become slow and dangerous. Overview screens, process mimics, alarm pages, trend pages, and heavy diagnostic displays must all be tested. And engineers should not test only the cleanest graphic. They should test the heaviest and most demanding displays, because that is where performance weakness appears, especially during startup, shutdown, trip recovery, valve lineup, sequence operation, and emergency response. The 12th engineering parameter is control command execution time, because a command must never feel like a suggestion sent into a void. When operators issue open, close, start, stop, reset, enable, inhibit, setpoint, or mode change commands, the system must transmit the command, receive confirmation, show intermediate states, handle timeouts, and represent success or failure clearly. A 1-second command execution target is aggressive but meaningful where field devices and communication paths support it. Commands carry consequence because they move valves, start pumps, reset alarms, change modes, enable sequences, and affect operations. So command handling must include select before operate, feedback, timeout logic, permissive display, command inhibit, duplicate command protection, and failure state clarity. The 13th engineering parameter is LAN loading, because SCADA networks require deterministic behavior, not average convenience. Network health is not only bandwidth, it includes latency, jitter, packet loss, broadcast traffic, switch loading, firewall delay, redundancy path behavior, storm control, and protocol efficiency. SCADA LAN loading should remain below 40% under the defined full performance scenario, because the network needs margin for alarm bursts, historian transfer, redundancy synchronization, client access, engineering activity, cybersecurity monitoring, backups, and abnormal communication recovery. A network running heavily during normal operation is already compromised before the abnormal situation begins. The 14th engineering parameter is alarm priority discipline, because 4 discipline levels such as low, high, emergency, and journal are usually enough. Too many levels create confusion, too few create poor differentiation, and alarm priority must be based on consequence, urgency, and required operator response time, not equipment importance alone. Every alarm should have cause, consequence, operator action, and allowable response time. And if an event does not require operator action, it should not behave like an alarm. Emergency alarms must not compete with advisory messages, journal events must not behave like process alarms, and low-value alarm floods must not bury the few alarms that actually require immediate intervention. The 15th engineering parameter is main control room to alternate control room changeover, because this is not only redundancy testing, it is business continuity and command authority testing. A 4-second or better changeover target may be required where operations depend on alternate control centers, and operators must know which control room is active, which is standby, whether commands are enabled, whether alarms are synchronized, and whether values are live. Poor control room changeover creates stale displays, duplicate alarms, missing acknowledgements, uncertain command authority, and confusion over who is actually controlling the asset. So engineers must test main control room failure, network isolation, server failure, client failure, command continuity alarm state, active standby indication, and recovery behavior. The 16th engineering parameter is recovery from alternate control room back to main control room, because recovery is often more dangerous than failover. Failover is usually tested, while recovery is often assumed, and that assumption creates risk when alarm states, historian continuity, command authority, event sequence, and user sessions must be reconciled. Recovery philosophy must be explicitly defined as automatic, manual, semi-automatic, or operator-approved, because faster recovery is not always better if it creates authority confusion. Controlled recovery is better than blind recovery, especially when commands are in progress, historians are backfilling, alarms are active, or network partitions have occurred. The 17th engineering parameter is normal to hot standby changeover, because a 2-second or better transfer proves whether standby is actually hot, synchronized, and operationally credible. A standby system that only exists in diagrams is not redundancy. It is a design assumption waiting to fail. True hot standby must preserve process data, alarm state, historian continuity, communication sessions, command status, operator visibility, and client reconnection under peak load. Therefore, the primary server must be failed during realistic operating conditions, not during an empty demonstration, and standby takeover must be verified without loss of critical state. The 18th engineering parameter is standby to normal recovery, because the recovered primary may have missed alarms, acknowledgements, commands, historian values, communication changes, and operator actions. It must not simply return, it must return correctly, reconcile state, and avoid resuming authority blindly unless the operating philosophy allows it safely. The 19th engineering parameter is alarm file storage capacity, because alarm and event storage is not just file size, it is investigation capability. 1 gigabyte may be a minimum baseline, but actual sizing must consider retention period, expected event rate, burst event rate, archive policy, backup policy, retrieval speed, compliance expectations, cybersecurity logs, communication failure records, operator comments, suppression actions, shelving actions, and recovery records. Small alarm storage causes overwritten events, weak investigations, slow retrieval, poor shift handover, and compliance gaps. So testing must generate the expected event volume, confirm storage growth, verify retrieval speed, prove archive behavior, and validate backup, and restore performance. The 20th engineering parameter is overall system availability, because 99.9% availability is not achieved by writing redundant server in a specification. Availability is an end-to-end property involving servers, storage, switches, firewalls, power supplies, time synchronization, virtualization hosts, clients, historians, backups, cybersecurity tools, patching strategy, spare parts, support contracts, monitoring, and operator procedures. Redundancy is a feature, but availability is the complete outcome. So failure mode testing must pull cables, fail servers, isolate networks, restart services, overload alarms, break communication links, restore backups, recover failed nodes, and verify that operators retain visibility, authority, alarm awareness, historian continuity, and confidence. This is where design engineers must become strict, because words such as scalable, reliable, robust, redundant, high performance, and future-ready have no engineering meaning until they are converted into measurable behavior. What point count was tested? What scan rate was tested? What alarm load was tested? What historian write rate was tested? What client count was tested? What CPU margin remained? What RAM margin remained? What LAN loading occurred? What failover time was proven? What recovery philosophy was used? What command response was measured? What timestamp accuracy was verified? What architecture was actually tested? This is how engineering replaces assumption. This is how specifications become protective. This is how FAT becomes meaningful. Do not ask only for claims. Ask for a performance compliance matrix, tested architecture diagrams, point count assumptions, scan rate assumptions, historian write rate assumptions, alarm burst results, redundancy switchover records, client loading evidence, network loading calculations, CPU and RAM records, degraded mode behavior, communication recovery behavior, firewall impact, backup impact, cybersecurity tool impact, and proof that historian logging was active during the test. A weak SCADA specification buys software features, while a strong SCADA specification buys verified behavior, and that behavior must survive expansion, communication failure, alarm storms, operator concurrency, server failure, control room transfer, historian backfill, network congestion, cybersecurity constraints, and the ordinary chaos of real industrial operation. For design engineers, instrumentation engineers, control system engineers, operations teams, and project managers, the mindset shift is direct. SCADA is not only screens, tags, alarms, and reports. SCADA is operational certainty, and operational certainty is engineered through performance parameters, architecture discipline, testing discipline, and acceptance discipline. Do not evaluate SCADA systems by appearance. Evaluate measurable behavior under load, failure, and recovery. Do not trust maximum tag counts without scan rate, alarm load, historian rate, client count, and redundancy context. Do not size servers from minimum hardware recommendations, because minimum hardware starts software, while performance hardware sustains operations. Do not treat historian sizing as storage arithmetic, because historian performance includes write rate, query speed, retention, compression, archive, backup, and recovery. Do not confuse redundancy with availability, because redundancy is a component feature, while availability is a complete system result. Do not ignore alarm bursts, because alarm storms expose weaknesses in system design, alarm philosophy, operator interface, server capacity, historian capacity, and network architecture. Do not make network loading an afterthought, because SCADA systems are only as reliable as the communication architecture carrying their truth. Do not accept demonstrations as proof, because demonstrations show capability, while performance testing proves suitability. Do not treat control room changeover as paperwork, because main to backup and backup to main behavior must be tested, timed, documented, and understood by operators. Do not allow procurement pressure to compress engineering judgment, because the lowest cost SCADA offer can become the most expensive operational weakness when performance parameters are not enforced. The best SCADA system is not the most marketed system, the most visually impressive system, or the system with the biggest theoretical number. The best SCADA system is the one that remains stable when operations stop being stable, when communications degrade, when alarms flood, when servers fail, when operators need clarity, and when performance is no longer optional. That is the standard, that is the discipline, that is the engineering lesson. If this helped you think more clearly about SCADA performance, like this video, share it with engineers who work on automation, instrumentation, control systems, operations, and project execution. Subscribe to the channel for more practical engineering design and implementation discussions, and follow my LinkedIn newsletter for deeper engineering breakdowns, field lessons, and technically grounded project insights.